next speaker this evening. I don't think he needs very much introduction. Let's bring onto the stage Alan Duffy.
Oh, thank you so much. So I just got a text that said my 5:30 a.m. start for a 6 a.m. on TV appearance was cancelled thanks to ScoMo changing his time of his press release. So, Sláinte.
You could have thought about that in the past.
What?
Or future.
Yeah, good one. All right. It's really weird when you get heckled by the organizer of the evening, but anyway. Okay, so I want to talk to you in the next 20 minutes about my field of research, that is dark matter. This is a mysterious, invisible substance that pervades the universe. Its gravity is responsible for us all being here today. But before we talk about the stuff that we can't see, I want to talk to you about the stuff we can. Does anyone know what this is? Shout it out. Nebula, good. By the way, I'm looking at my PhD students. I'm not hearing anything from there. Okay, very good. Yes, this is a cloud of gas and dust, tens of light years high. We see these columns with this Hubble Space Telescope image that essentially, is this a laser pointer? No, it's not. Wonderful. That darkness, just picture, I'm just going to wave dramatically. The darkness is blocking the light from newborn stars like our sun. Deep in that dark, cold gas and dust, new stars are born. Some of those stars are incredibly massive, incredibly bright, and from the fury and energy of their starlight, they rip apart the environment that gave birth to them and reveal themselves to this image. In particular, we see these OB stars, these beautiful blue stars, distributed around that nebula. We can zoom out to such a scale now where the gas and the stars, they all merge together into a collection that we call a galaxy, composed of billions of stars, now merging into this faint, uniform glow. And again, we see the dust lanes now on a galactic scale blocking that starlight. And if we then turn our most powerful telescope, the Hubble Space Telescope, and we point at a patch of the sky with, at least to our eyes, nothing present. An area no larger than your thumb outstretched, and we just open the camera, then over the course of a week, this image is revealed. Photons raining in, light accumulating on those sensors over the course of that week, to reveal an image of thousands of galaxies, every single point of light, an entire galaxy on its own, stretching all the way back to the observable edge of the universe. If so many galaxies are clustered into just such a small patch of sky, it means that our universe is littered with galaxies, and all of those galaxies containing stars and clouds of gas and dust. So many stars, the number is above a sextillion stars, a number I had to look up for this talk. In other words, there's a lot of stuff. And yet what I want to argue tonight is that there is 5 times more of this invisible dark matter than every single atom in all of those stars and clouds of gas and dust and all of those galaxies put together. And you're going to help me find it. So, right now, the dark matter is in this room. And in fact, the dark matter is actually throughout our galaxy. As we'll soon see, it's the gravity of the dark matter that indeed holds our galaxy together. So we are in a cloud of dark matter, and our sun is traveling around the galaxy through that cloud. Now, if anyone has driven in the rain falls vertically. But as you drive through it, it looks at the, especially at night, looks at the last second where that rain rushes towards the window screen. That's the headwind effect. That's, of course, you going through it. And in the same way, our sun is going through the cloud of dark matter. So we know that we should experience this rush, this headwind of dark matter towards us, or rather, we through it, just as the car through the rain. We are moving through our galaxy in that direction. Cygnus is directly above us right now. And that means there is a cloud of dark matter sweeping through us. So we're going to do an experiment. Could everyone give me the OK symbol? All right. This is going to, and you can close your fingers if you like. This is it's an inch across, an imperial, a couple of centimeters across. If you could then angle that upwards towards the sky, and then with the other hand block that funnel. And now, if you could all count after me, we're going to count down from 5. 5, 4. You're supposed to count 3, 2, 1. Well done. Who caught some? Did someone catch some? Has anyone caught some? Did you catch one? Did you catch anything? Anyone catch it? There's a hand left. No, okay, you're good now. Okay. You really should have. You really should have caught a particle of dark matter. Every one of us had 500 million dark matter particles just pass through our hands. I suspect none of us noticed. Don't worry, you'll get another chance. So you're all scientists or scientifically literate or interested in science in some way. You should, I hope, all at this point be pretty uncomfortable with this idea that I've just been spouting, that there is this invisible side to our universe. Essentially, an amount as large of dark matter versus what we can see as, say, an iceberg, where the vast depths of that iceberg is below the sea level, and all we see is the top. In a weird coincidence of nature, which means nothing, that fraction is exactly right, 17 and 83%. Don't know why. No one knows. It means nothing. Now, I just really love the fact that the fraction of the iceberg above the waterline is the same as atoms versus dark matter. Anyways, again, it means nothing. So how could we possibly take this idea seriously? It is pretty fantastical. It's pretty crazy. Well, we have this legend to thank. This is Vera Rubin. She decided to go, an American astronomer decided to go and weigh galaxies. And the way she did this is kind of neat, and I need a volunteer. Show of hands. I need seriously, someone come on. Oh my God, how much drink have you all had? And no one's going to come and say, yes, all right, come out of the front. Thank you very much. Round of applause. Oh, it's the former speaker. No, sit down. You don't get to come up. Got to share the love. All right, this side of the room. Come on, someone hand up. It's not that terrible. No, you're my PhD student. That's embarrassing. Yeah, all right, up you come. Thank you so much. Round of applause for one person who has bravery. Okay, your name? Flores, thank you so much for coming on. A round of applause again for Flores. He's going to help us with this experiment. Okay. This, once upon a time, was my dog's chew toy. It is now a highly scientific experiment. So Flores, what I want you to do is just to spin this around. Okay? Just that. All right. Okay. Don't applaud that. I'm not saying my dog could do that, but still, come on. Okay. So Flores, what I want you to describe is, to make that rotate around, there's a certain amount of force, right? You're having to spend a bit of force. Okay. I want you to now spin that faster. Keep going, faster, 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 faster. More faster, faster, faster. All right, is that more force or less force?
More force.
More force, excellent. Okay, all right. No, that's good, that's good. No, we got that bit of the experiment done. Okay, we can slow it back down, slow it back down. Okay, it's a marathon, man. PhD is a marathon. Okay, slow again. And now what I want you to do is make the string longer. Make it as long as you can, and keep the rotation. And now I want you to make that go fast, 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 fast. Keep going fast, 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 faster, faster. Come on, Flores, go faster! Is that more force or less force?
More force.
Excellent. All right, there we go. Round of applause for Flores. Thank you, Flores. You have demonstrated Newtonian dynamics. Thank you so much. And that is science, people. All right. What Flores has just demonstrated is that for an object to exhibit orbital motion going around and around and around, the faster you go, the more force is required to hold on to it. And indeed, the faster that goes and the further away that is, the even greater force that's required. And what happens if that force just disappears? Then off it flies. So glad that didn't hit anyone. Okay. That's the key. In space, what do we have? We have stars whizzing around. What force do we have to hold on them? They're not strings in space, of course. There's gravity. And gravity just depends on the mass. So in other words, if you see something that's moving around fast with a lot of force holding on, must be a lot of gravity, must be a lot of mass. You have weighed the object inside. Even better, as you go further out, you can build up that measurement of the mass. So, that's exactly what Vera did. She measured stars here, here, here. She did a plot of the speed that they were going around as a function of their distance. And what we expect to see is that all of the mass is that bright stuff in the middle, all of the stars. They have a lot of force. They can hold on to fast-moving stuff. But you need so much more force to hold on to things that are very, very far away and yet still traveling very fast. And if you don't have that force, if you don't have the gravity, then off they fly. Those fast-moving stars would literally fly away. We shouldn't expect to see them. That is what we thought we would see, that Vera thought she would see. And instead, this is a science talk, so you have to see a plot. We see the exact opposite. That stars are in fact moving slowly and in fact get faster the further away they are. The top curve is what we see, the bottom curve is what we expected. The difference, those incredibly fast-moving stars at the very outskirts, to hold on to a star that's moving that fast requires tremendous amounts of gravity, tremendous amounts of mass. In fact, 5 times more mass than everything we can see put together. It's mass, it has gravity, it must be matter, but we haven't noticed it. It must be dark. And in fact, because the stars keep speeding up, and indeed gas on the very outskirts of the galaxy itself, that dark matter must extend to these huge distances. So that's how you weigh a galaxy, and that was our indication that there was something missing, a darker side to our universe. But because the dark matter has mass, its gravity, of course, is what we're seeing, or the effects of it, the unexpected motion of these stars and gas pulled by the gravity of an unseen companion, we can use another property of that gravity. This is a prediction by Einstein. It's called gravitational lensing. And this is a map of the dark matter, and I'll quickly show you how we do it. If anyone's got a wine glass, you could play along. You need a piece of paper. You need to draw a dot on the piece of paper. Don't expect you to do it. We also don't have time. I've just seen the thing. All right. So I did it for you. Here's a piece of paper with a dot on it. We're going to put the wine glass on top of the dot. The wine glass will lens that image of the dot in just the same way as Einstein's prediction of the mass of this dark matter would lens or bend the light of that background image. So there we go. That's what a wine glass on top of a dot looks like. And now I want you to pay attention to this experiment I did. Look, when we're looking directly down the wine glass, what happens to the image? When we're off to the side, we move around. That background image of the dot changes. And then, just to show there's no tricks, there we go. We take the lens away. So Einstein's theory tells us that this mass can bend, can lens the background images. So we should go out and expect to see that, right? So what happens when we are in perfect alignment? Us, the wine glass, and the background image, the blue dot, all in a perfect line. What does that look like? What happens to the dot? It disappears. Any other advances? If my PhD students don't get this right. Yes, Adam? It gets brighter. It does. There's another more obvious thing that happens that we're going to talk to you about tomorrow. Okay. Circular. Yes, thank you, whoever just got Adam's PhD scholarship money. All right. That's right. The background dot, the image, now becomes a perfect circle, a ring. We can see through the stem, we can see the original image, but now we can actually see that background image, that dot has become a circle. And I'm telling you that the mass of a galaxy can do the same lensing that this stem of the wine glass can do. So we should see this optical illusion, right? If we go looking into the night sky. And that's exactly what we find. The red is a massive galaxy that lies between us and this background blue face-on spiral. Looks like that blue dot I drew, except now we're in perfect alignment, or near perfect alignment, and we get what's called an Einstein ring. But that's a very unlikely sequence to be in such a perfect alignment. It's far more likely that we're kind of looking at a slight angle. So what happened to the background dot when we were looking at an angle? Did anyone notice? I literally could not have prepped you anymore to pay attention. What happens to the background image when we're off to the side? Yeah, you get the warps. There's a bit of an arc. So we get this giant arc on this near side and a little arclet on the far. So we do the same again. We go out and we look. But this time we're going to use a cluster of galaxies, a giant group of galaxies. All of those red objects are part of this massive object, and there is our giant arc, one side, the little arclet. But because this is a complex structure, many wine glass stems essentially dotted around, we see these little arclets all through the image. And indeed, it's using that knowledge, being able to, through powerful supercomputers like we do on OzStar at Swinburne, we can invert. We can essentially place multiple wine stems until we recreate that image. This is a technique called gravitational lensing, strong gravitational lensing, and here we see the light rays bent around the curved space-time deformed by the mass of the cluster of galaxies. It's as simple as that. And using that technique, we can turn the positions of all those galaxies and the dark matter around them into the map I showed before. So now we can see the invisible betrayed by its gravity. So, I told you you'd have another chance to catch dark matter. And congratulations, in a room this size, in the last 20 minutes, statistically, one of you will have had an atom knocked out of your body by that wind of dark matter. Well done. Now, you didn't notice it, and if you did feel anything, it's possibly gas from too much beer. And that's because we make for very bad dark matter detectors, but we're building a better one. It's made from a crystal of salt, sodium iodide, not something you should maybe put on your chips, but a crystal of salt nonetheless. Ultra pure, and it will glow when struck by dark matter. We're putting that into a large vessel, 10 tons worth of scintillator around it, and we are taking that crystal observed by highly sensitive cameras, and we are taking that deep underground. And we have to do that because our bodies are constantly bombarded by radiation from space. We call them cosmic rays. Hundreds of these strike your body each and every second. They would blind our detectors. So we take them deep underground, the bottom, in this example in the UK, in Bulby, kilometers underground, where that rock layer protects the detector from this radiation from space. The dark matter, on the other hand, just flies straight through. It's a ghost, essentially doesn't interact. Hopefully, however, of course, occasionally colliding with the detector. You have to worry about what you build your detector out of. So some of these experiments have gone and taken sunken vessels, ask me about that later, sunken vessel steel, which has been preserved deep in the ocean, or even ancient galleys from Rome, to secure the most clean and precise materials to build the detector from, so essentially it doesn't see its own radiation. And we are doing all of that right here. This is the gold mine in Stawell. That's the gold mine. I knew you all knew that, but that's the gold mine. It's an active gold mine. And in a project led by Professor Elisabetta Barberio of the University of Melbourne, a team of universities from around Australia and the world, we are going right now excavating the underground lab, a kilometer underground. We will place a dark matter detector at the bottom of this gold mine with a crystal that will glow when struck by a ghost. And we are doing that to try to understand this mysterious substance that makes up 5 times more of the universe than everything we can see. And if that project hasn't made you want to sign up for a PhD like my 2 students there with me, I don't know what will. Thank you very much.
Thank you, Alan. We'll take a few questions. It's okay. He won't fail you. Yeah.
Okay, so that's a great question. So the question was, the idea that we're moving through it, so we get this headwind, what's to stop it being actually co-rotating, moving with us, so we wouldn't see anything? So to a certain extent, our gravity of our disk, the stars and the gas that make up the plane of the Milky Way, will drag a little bit of the dark matter along with it for the ride. But most of it is essentially a cloud of just random motions in every direction. Its inability to collapse essentially into a more concentrated form, to form like a pancake-like disk, that's the key difference between us and it. It can't lose that energy. It doesn't shine light. It can't get rid of that energy, essentially. So the idea is that the simulations, all the theoretical predictions are very clear. For dark matter to both be invisible means it must also essentially move in this random motion through and around our galaxy. So for all intents and purposes, when we work out the calculations of us moving through it, it's static, and it's our motion through it that counts. But there will, well, some simulations, some people, so you can run these supercomputer simulations, that's what I do. Some simulations do suspect there's a dark disk that follows us, pulled by our gravity, but I think they're wrong. So, yeah.
We've got a question over here.
So I've been, by the way, I was the one who answered the circle. So I've been following, like, I developed interest in dark matter, in quantum mechanics.
Okay.
like just last week when I started watching some videos of Neil deGrasse Tyson.
Okay.
So it's really interesting. So my question is there a link between dark matter
Yep.
and protons that go in and out of existence when they move? That can be anywhere at the time, and also the dimensions of space. Like for example, other dimensions of space that is not visible to our eyes, but
Okay.
that science has confirmed they exist. So is there any relationship between the large stuff that we observe in the galaxy and
Right.
small stuff that happens in the cell, like the protons?
Okay. All right. I'll try to paraphrase that. So is there a link between these large-scale distributions of dark matter, these large properties, and the small-scale behavior, so extra dimensions that are wrapped up into smaller scales, or new types of subatomic physics? The answer is yes, and it's going to be tricky to tease out that exact connection, but why we're so excited by dark matter is the fact that it is a signpost on where to take our study of the deeper, more fundamental description of the universe. At this point, the standard model of particle physics, we found the Higgs boson, the God particle. Show of hands, who's heard of that? Yep, okay. Essentially completed the jigsaw puzzle. That's it. That jigsaw puzzle, which is gorgeous and wonderful, and my particle physics friends are all great for doing it, doesn't include gravity. Seems like a miss. I don't want to slag them off, but, and doesn't include dark matter. But with dark matter, if we were to understand, if we were to detect it in SABRE, led by Elizabeth, that would be a sign of where to take our theories. You have to be able to explain this new thing, and then we can finally advance that description of the subatomic world. There are theories that suggest there is a dark sector, so the dark matter is doing its own whole thing. We are unaware of it because we can't see it, and there are other theories where extra dimensions can play a role in that, but at this stage, the simplest theory is the dark matter is a type of particle 10, maybe 100 times the mass of the proton in the hydrogen atom, so essentially something the weight or atomic mass of something like iodine. That's why I build a detector with iodine for efficient detection of that. And that's essentially all we know about it. It's kind of weird to know exactly how much and exactly where something is. We have no idea what it is. And yet we've done this before. A century ago, essentially before the atomic theory, there was this invisible stuff, we call it the air. We could see its motion, the wind moving the trees, so we knew it was there. We just didn't know what it was until we finally could begin to explore atoms and ultimately split them. That's where we are. We can see the effect of the dark matter. We just don't know what it is yet. And Australia, I think, has the best chance now to uncover the nature of that dark matter, because we just had announced the Center of Excellence for Dark Matter Particle Physics, $35 million over 7 years, that will put Australia foremost in the world on the search to explain more of the universe than all of our efforts in astronomy to date. That's what Australia's going to do. It's pretty cool, right?
We'll take one more question.
I was going to say, can I have,
Yeah, you can pick.
like a woman ask a question? Or just super... Hey, how's it going?
Given the current testing, what is the prediction of soon this crystal be active to detect dark matter?
Ooh, so how soon will we detect dark matter with this crystal? There is an experiment in Italy that has claimed to have seen dark matter. And we are the only the only experiment in the world that can test that directly, because we're on the Southern Hemisphere. I didn't get a chance to explain what's called the annual modulation, but buy me a beer and I will afterwards. In 3 years, we will either see what they have seen or we will rule it out. Either way, we'll have done a huge service to science. If it's the former, we've discovered dark matter, and we get a fight for the Nobel laureate, I guess, between us and them. And if we rule it out, we rule out this entire swathe of possibilities for dark matter and help refocus efforts everywhere else. And I suspect that group never sends us a Christmas card again. But that's what it means to be just hunting in the dark for this thing. We don't know what it is and how massive it is. There's 35 orders of magnitude of possibility. The new Center of Excellence will span a lot of that. But for me, as a scientist, it's exhilarating to know there is so much potential out there and that you can make such an incredible mark on an advancement of human knowledge. To be part of an experiment like that is truly remarkable. And for my mind, it is only possible in Australia where we have a somewhat more egalitarian streak in science. We can more easily get into these experiments. We can be part of these efforts. And I guess I just think back to the fact that we're doing all of this in an active gold mine, the most precise, clean measurement in history, certainly in the Southern Hemisphere, and it's in the bottom of a gold mine, and you have to like wear hard hats and shit. And I just think I never would have seen my career be this. That's why science is awesome. That wasn't your question at the end, but I still think it's worth saying. Science is awesome. 3 years. Yeah. So call me in 3 years, and I'll either be, well, I'll be celebrating either way. But maybe some of my Italian colleagues won't be. Yeah.
Thank you so much. Call Alan in 3 years and
Thank you.
where we're at. Thank you very much, Alan. Well, don't forget we still have a draw prize to draw tonight with so make sure you get your tickets out, see what your number is. But before we do that, what do we have?